I wanted to talk about the evolution of the AMSAT flight software. And by the way, when I say AMSAT, of course, as Hans said, I'm speaking of AMSAT North America. I am a life member of AMSAT. I volunteer leading the flight software development for our Gulf satellites, and have done that all the way from since the beginning of the Fox satellites 15 or so years ago. So thanks for inviting me to speak at the AMSAT South Africa Symposium. And now I'm having the trouble. There we go. As Hans said, thank you to AMSAT SA and SARL members for the wonderful reception I got. And it was actually only last year that I was lucky enough to come to South Africa with a singing group. And I took a day off to visit, and it was a joy to see so many of you in person. So innovation, the theme of the symposium is embracing 68 years of innovation in amateur radio. And I'm going to talk about the evolution of software in the AMSAT North America satellites in the past 15 years or so. I kind of think innovation is a form of evolution. So many things are made from standing on the shoulders of giants, as Sir Isaac Newton has once said. And in fact, I was kind of fascinated about the AO7 stuff, which I've heard a lot about, but I've never seen that video. And in fact, our Fox satellites that were first launched in 2015 also had photon-powered rotation and magnetic attitude control. So that is all evolved also from AO7 and probably before that. So it was great. But just examples of innovation in personal communication, we've gone from drums to telegraph, to telephone, to ham radio, to CB radio. And then if any of you remember the big suitcase-sized mobile phones that went to flip phones, that went to iPhones. And I could even talk about things that merged in there, like Windows computers going to iPhones. So anyway, I'll be talking about the evolution of software in AMSAT's CubeSats. And again, why is this not clicking? There we go. I started working on the Fox software somewhere around 2010. I'd worked on a commercial operating system for 30-some years before that. So even my first try at flight software evolved from something else. I have to shamefully admit I didn't pay enough attention to previous satellite software. But that's where I went. So Fox 1 was our first set of CubeSats, and they were 1U CubeSats, 10 centimeters by 10 centimeters cubed. They had simple FM repeaters, 200 bits per second data under voice telemetry. So this is why when you use them, you could always hear a kind of a noise under your talking, because that was the data. And we had very few slow commands that were uplinking. In 2021, we launched Fox 1E, the fifth of the Fox satellites, and we changed to linear transponder. We changed to 1200 BPS, bits per second, and it's BPSK, binary phase shift keying telemetry. We added whole orbit data, and we added 1200 bits per second secure commanding. HuskySat-1, which was the University of Washington satellite that we had our radio on, and that was launched in 2019 to the space station and launched from the space station in 2020. But that added a CAN bus. MESat-1, which was mentioned in the video of AO7, was the University of Maine's satellite that again had our radios in it. That was launched as as the gentleman on the video said, in 2024, on July 4th, it turned out to be the same day that I was leaving for South Africa. And that was the beginning of our software kind of branching to a generic LTM and Fox Plus, and I'll talk a little bit about those later. And now we are working on the Golf satellites and Golf T. We don't have a date for launch yet, but that added a different processor, the IHU. For some reason, we call our processors radiation tolerant IHU. Multiple processor coordination, attitude control. We have a GPS, and we have a new power system on it. So let's go through a little bit more of those in a bit of detail. Actually, let me talk first about what's going on with or what happened with the Fox software. Now remember, though, that nearly everything in the first Fox satellites has carried over into the latest satellites. Excuse me. Since the first Fox that I worked on, we've had a real-time operating system called FreeRTOS. And it's a really kind of a simple operating system that supplies only a few things: tasks, timers, queues, semaphores, or mutexes, which are nearly the same thing. But there's no support for device drivers like we might be used to in many operating systems. For example, buses, terminals, radio, that all had to be written by us. One thing that's critical for use with an OS that has multiple tasks, devices have to be interrupt driven. Now, it's fairly common in the past that simple software would just be a loop that runs round and round and round. And you look and say, okay, I'm going to do this next, I'm going to do this next, I'm going to do this next, and then you loop around again. But for an operating system, the software can't loop. It can't loop while it's waiting for a device to finish. But the big advantage of that is that a task gets to run when it needs to run, as opposed to just in order on this loop. So the general path of the tasks are that the task calls the device driver to ask for, let's say, the temperature. Sorry, this is the general path for a driver. The driver sends a command over a bus to the sensor. Hey, give me the temperature of the whatever. The device driver waits for a semaphore to say that the device has been returned. And when it's waiting for a semaphore, other tasks can run. And in the meantime, when data is returned over the bus, the device forces an interrupt routine to run, and the interrupt routine releases the semaphore. So now the next time that the task that called the device driver runs, it can continue on and get that data and do whatever it needs to do with it. So examples of device drivers are I2C, SPI or SPI, and serial line CAN comes later, but they're all various device drivers. So let's, I just want to look at the software tasks that exist, and you'll see that these change later. The tasks that exist in Fox 1A through D are, there are 6 of them. The diagnostic task that just runs a terminal console that we use for testing and debugging before flight. It's not really used in flight, although it's still there, largely because removing it means that what we're testing isn't the same as what we're flying. There's a telemetry collection task that runs every few seconds and reads all the data from the devices that we want to put into telemetry. things like temperature, voltage, current, and various states. It also runs them through a min-max algorithm that saves the latest values to be downlinked on request. Downlink control determines what telemetry will be sent when, and when the repeater is to be turned on. For example, in safe mode, only 2 frames of data are sent every 2 minutes. The repeater is turned off, so that is saving a lot of battery power. RxTX control is in charge of the receiver and transmitter. It also collects telemetry from the downlink control, modulates it onto the FM carrier, and requests the next packet from downlink control when it's done. Commanding runs when an uplink command is received. It decodes and executes it. And experiment control runs any third-party experiments we might fly. Golf T, a number of the Fox experiments plus Golf T have radiation testing experiments from Vanderbilt University. So what does a task do? How does a task work? So this is the what happens in a generic task. And nearly every task works this way. First, it waits for something. A trigger happens of some sort. It does its job. It uses the trigger value to do the task's job. And then the task might also wait for I/O, for example, while it's doing its job. So it might look like a loop without an OS, but the key word is wait. While one task is waiting, other tasks can do their own work. So what might it wait for? It might wait for a timer. Telemetry collection is an example. Telemetry collection works waits for about every 4 seconds, and then it goes to all the devices with telemetry to collect data. It might wait for a message from another task. Downlink control is an example of this. It waits for a message from the transmit task to ask for more data. And it looks at the current mode, decides whether it's time to send data and what data. And it might wait, a task might also wait for a device interrupt. And the command task is an example of that. It gets a device interrupt, or actually a message from the device interrupt, saying that there is an uplink command of some sort, and its job is to decode and execute that command. The downlink is, I'm just going to talk about that particular task a little bit, because it's the most complicated task. The downlink control task is responsible for implementing modes like safe mode, health mode, science mode. Safe mode, as I said, only runs telemetry every couple of minutes, and it has a lot of things powered off to save power. Health mode has a number of things, including the transponder, powered on, but you can also decide exactly what to turn on. And science mode, which sends more science data and less health data. It's responsible for switching modes based on commands, on timers, on internal state. And it's responsible for formatting telemetry according to the mode and when it's required by the transmit task. One thing that is very important that it does is to calculate forward error correction. And in particular, we use Reed-Solomon 223-255. It's quite amazing how many bits this particular Reed-Solomon can recover when they're wrong. We also do send a checksum of various kinds because Reed-Solomon can only do a certain number of bits. And Reed-Solomon isn't perfect. It can somehow fix the bits incorrectly. So that's the that's most everything, but so it's most everything that's in the Fox 1 A through D satellites, and it continues on to the rest. But the first major evolution came in Fox 1E, which launched in 2021. That was the change to linear transponder from FM. It was a change to 1200 bits per second BPSK telemetry, and it added whole orbit data. So whole orbit data saves telemetry every minute, and it saves it into memory so that it can transmit it later. So it, for the most part, we can have telemetry data from the entire orbit. And it added a new kind of commanding, 1200 bits per second, secure commanding. So here's that software task diagram again. You don't see much change here, but RxTX control is now using a hardware modulator for BPSK. Commanding has more decoding to do, and telemetry collection, in addition to its previous task of collecting telemetry, also saves the whole orbit data in a circular buffer in non-volatile RAM, MRAM, for later transmission. The biggest change, though, is downlink control because of all the additional telemetry. And you remember, downlink control is the most complicated one to begin with. So the telemetry I want to talk about a little bit and how that works in Fox 1E and in the future. 1200 bits per second allows 6 times as much data as we had in the first 4 Foxes. So what do we do with that data? The main thing that we did was to add whole orbit data. And to add whole orbit, I think I'm going to say a little bit more about whole orbit data. I guess I'll say it now. We repeat the same, we save data every minute, and we keep repeating, transmitting that data that's been saved over and over, except that every minute we add a new, add the newest bit of data and delete the oldest. So and in this circular buffer. So we rather hope that we will get most of an orbit's data. I believe we have enough data storage for 2 orbits worth. So we added the whole orbit data, we added multiple downlink frame types, and we added this terminology called payload. So what does payload mean in terms of telemetry? Here it is. Part of evolution is keeping things that work. And both the flight and the ground software expect fixed size frames of data. And a frame is what's sent down with the forward error correction. And we don't want to mess with that forward error correction that works so well. So we keep the frames that are fixed size, use Reed-Solomon and what we call 8B, 10B encoding. I didn't mention that before. But frames now have a variety of types, and those types are what we call payloads. So if you see, I think you can see my my pointer here. Header. This is frame type 1 that contains a header that tells you which type of frame it is, along with the time and so on. And within that frame, we have payload type, frame type 1 has payload type 1, payload type 2, and payload type 5, for example. And some filler, because the payloads never seem to add up exactly to the size of our frame. Now look at payload header type 2, and again, it has a frame. The frame includes the information that it's type 2, but Frame type 2 has two copies of payload type 2 and a payload type 4. So why would we duplicate type 2? The reason is because type 2 is whole orbit data, and each type 2 frame is is a different one of those circular buffer entries. So we want to send lots of payload type 2 in order to keep transmitting that entire circular buffer of whole orbit data. So that's the difference between payloads and frames. A frame is a fixed size that contains multiple payloads, and the payloads, there may be duplicate types of payloads, or there may be all kinds of different types. So we started using that newly in Fox 1E. So university satellites, the LTM stands for Linear Transponder Module, but we're thinking to try to change the name, like UTM, University Transponder Module, I don't know. But anyway, the simple idea was that this is a win-win for us and for universities. They provide experiments that they want to fly. They provide power, they provide the space frame, and the students to build this thing, and they do all the paperwork, right? They get the grants to launch and so on. We, on the other hand, provide the radio for telemetry and commanding, because that's one thing that they don't particularly want to do. We get amateur linear, and our win is that when they're done, we get an amateur linear transponder that they might turn on while they're doing their experiments, or they might not turn it on till they're done, but nonetheless, we get it, and it's great. This is what it looks like. It's just this actually has four boards, but the LTM is a 3-board set. It's got the processor on the top, it's got the transmitter board and the receiver board. So we are thankful, by the way, for HuskySat, which is the University of Washington, because they were the ones that gave us the information, the idea of using the CAN bus in a satellite. So the CAN bus is the next form of evolution of software and hardware, in fact. University of Washington was using CAN within their part of the satellite. They wanted to use it to communicate with the LTM. And it's been used in automobiles for decades, but it was new to us as a spacecraft bus. So that's what we decided to use, and it's been great. We've used it a lot since then, and you can see with this task list that it has added a 7th task. Why does it need a separate task? And the answer is because tasks are autonomous. They can run at any time, and can, unlike I2C, SPI, Serial, any device on a CAN bus can start a transaction. So in other words, from the point of view of the onboard computer, a message can appear just totally asynchronously. So the CAN task's job is to receive that message and distribute it to the task, typically sending one of these other tasks a message where it's supposed to go. So our next plan originally was going to be Golf T, which you will see in a minute. But we had a lot of Golf delays, and we decided that we wanted another satellite sooner. So Fox Plus came into being. Fox Plus A will be a lot like Fox 1E, but with commercial power and satellites. Commercial power and antennas, and got satellites on the head. So our hope was to get this done a lot sooner than Golf T. But we also have AMSAT 1. Let's see, is this going to work? No, I guess I did not have the clever little clicky thing. But anyway, the next we also have MESAT 1 at this point, and from a block diagram point of view, these are pretty similar to the previous slide. But I only mention them because the evolution sort of branches here. The code for Fox Plus, as well as future LTMs, is based on MESAT 1 with a lot of customization removed and some generic code added. So Fox Plus will also have to have code to support, and this is basically drivers, to support the ISI space power supply and antennas. And in fact, we brought back a driver from University of Washington because University of Washington also used the ISI antenna. So again, we are reusing as much code as we can. Okay, so let's talk about the current evolution, current evolutionary state. This is a picture of a plastic version of a 3D, well, not surprisingly, since it's 3D printed, that it's plastic. But Tom Karnauskas, one of our mechanical engineer volunteers, built this so that we can look at this and just get a general idea of what Golf T is going to look like. Golf T is going to be our first 3U CubeSat. This is the transverse stack here. It's set across the width of the 3U satellite. And I believe it's these three boards here. And plus, these three boards are essentially an LTM. This board here would be the, or maybe it's this one, it's actually the Vanderbilt University experiment. We have a GPS here. We have a microwave. This is 10 gigahertz SDR downlink radio. A whole bunch of other stuff, including this RF matrix, which is kind of switches that send the RF to the correct antennas, power supplies, an attitude control system. So this is the hardware stuff that was added. You can see there's just an enormous amount of new stuff in Golf T. So I want to talk a little bit about one of the new hardware pieces here. This is called the RTIHU. IHU is Internal Housekeeping Unit. I don't know why we use that term. It means the onboard processor, onboard computer. We hope it's going to be more radiation tolerant. And the reason is because the processor chips are automotive grade. They're not actual hardened radiation chips. Those are really expensive, but they are automotive grade. Automotive grade processors tend to be somewhat radiation resistant. You don't want a cosmic ray to break your brakes when you're trying to slow down. So they are a little radiation resistant. Plus they have EDAC memory. That means that it's let's see, what does EDAC stand for? Error detection and correction memory. Parity on buses and redundant cores. Each one of these chips has a redundant core that's mounted at 90 degrees to the other one, and they go in lockstep to check each other. And on top of the two redundant cores, there are two board halves. So you can see right down here, if you took a line in the middle, these sides are very similar. And right here are switches, bus switches, that decide which one of these processors is in charge at any moment. They switch the processor to connect to the bus that connects to the rest of the satellite. So each redundant board half has a processor chip. It has non-volatile memory. It has a command receiver and transmitter and telemetry transmitter. And either one can double as the other. And as I mentioned, those bus switches to keep the failed side, a potentially failed side off the satellite bus. So this is a brand new board. We thought it would be a good idea to have a processor with space experience. Right, so on top of everything else, we also have an LIHU, that is the same processor that flew in all the Foxes, Husky, and AMSAT 1. So in effect, Golf T will have 3 onboard computers that the software has to coordinate. And if you are want to go back to the 2020 AMSAT North America Symposium, I talked about how all that works, and I'll say a little bit about it in a minute. Another bit of hardware. As part of my trip last year, as well as visiting you folks while I was in Johannesburg, I also visited CubeSpace while I was in Cape Town. So besides having a nice tour and getting some questions answered, I met our main contact. And it's always a nice thing to meet people in person. Both Wade at CubeSpace and all you guys whom I met last year in Johannesburg. It's great to have that face-to-face contact. So our attitude detection and control system is built by CubeSpace in Stellenbosch. It does use CAN as the main access bus. So again, thanks to University of Washington for poking us a little bit and getting us to use the CAN bus. So it does attitude control system. Why do we care about attitude control? Heck, we had those magnets in the previous satellites. Well, the reason we care is because it keeps the solar panels pointing at the sun. Because we, on this satellite, actually have solar panels that unfold. So it's 1U, but we actually have 20 centimeters worth of solar panels on each side. So we have satellite, let's see, 10, 20, 30, 40, 50 centimeters worth of solar panels by 30 long. So we hopefully have a lot more power if everything works as we hope. So it will keep the satellite panels pointing at the sun, or we also have a 10 gigahertz planar antenna, and when we're using that, we want it to be pointing at the Earth. So that's what our ADCS is going to be used for. So we have a few new processors here. We have the CAN bus down, that actually should have been the CAN bus, I think. Anyway, we have another processor. Oh, sorry, this is not, this is the hardware bus. Excuse me. That's why I was confused. So this is the block diagram of Golf T. We've got the processors here. We've got the RTIHU, and the 2 RTIHU processors talk to each other on their own private CAN bus, as well as to the main CAN bus. We've got the CIU, which is the central interface unit. We've got so much stuff. We need a board to connect everything. We've got the microwave radio. We've got the GPS system, the GNS system, CubeSpace, ADCS, and the power system, all talking to each other on the CAN bus and a few other things. The CIU, by the way, has its own processor on it because it has a lot of I2C A to D converters that the CIU processor will read and send to us, send to the main processor on CAN. So I haven't even mentioned the most complex part. You can see that each one of these require some OBC software to support it. And the Golf T software is therefore a lot more complex. But we'll talk about the most complex part in a minute. I just want to show you, here's the new, here's the software block diagram that you saw before. We have 3 different processors on board for redundancy. So if 2 fail, the remaining one has to be able to do everything. So for the most part, we can't just assign different jobs to different processors. We have to designate one processor as in charge. But we also have to have one of the others take over if the in-charge processor fails. On top of that, we need to keep all the processors in sync so they have all the same data. So for example, the whole orbit data, we don't want to lose the data that one processor saved if it fails and switches over to another one. So how do we do all that? How do we do all that? There we go. We have another task, which you might guess. It's called processor coordination. This task watches the processor information, notices if one fails, decides whether the processor it's running on will be in charge, and then forces the other processors to do the switchover. But, relative to this talk, the point here is that despite all the new complexity in Golf T, it really uses the same basic software as the original Foxes with these 2 as new tasks. So I want to mention, I just want to say what the, kind of a summary of my ideas of software evolution. It has some advantages. It avoids reinventing the wheel, right? There's a whole bunch of software that I did not have to write in Golf T because it was there before. It speeds development a lot, although you'd be surprised to hear that if you learned that I've been working, I and a number of others have been working on the Golf T software for, I don't know, 4 or 5 years now. But certainly bugs have gotten found in previous versions, and we haven't carried those over because we fixed them before. And in fact, the whole thing feels more familiar both to users and to software developers. So it has a lot of advantages, reusing software. It has disadvantages too, though. If we say, oh, yes, I'm going to do the same thing I did before, then that means we don't have to think of new approaches, and that means we may miss some better approaches. That is surely true, and one of the big disadvantages to totally reusing software, or anything else for that matter. Adding features to existing software that weren't planned from the start can make code messier and harder to read. And that is not only true on my on the flight software that I've been working on, it was certainly true in my work software too. I think we were on version 8 when I left. And occasionally I would look back at version 1 and see how much simpler and easier it looked. It's true here too. It just gets messier and messier because you had some beautiful module that you saw that was so simple, the first one. And then when you change it a little bit, you add something here and you add something there, and it's just a lot messier. And indeed, sometimes you depend on some infrastructure, like compilers, and they can go end of life. I think I have changed 2 or 3 times the processors, the compilers that we used, because the manufacturer decided to change how it worked. And when you change the compiler, not everything that you wrote in software works exactly the same. It's supposed to be the same language, but it doesn't work exactly the same. It will optimize things somewhat differently, for example, and you don't realize that you depended on the way the compiler worked, even though you didn't intend to. So those are the disadvantages that I see. Um, I don't remember if I mentioned this before, but in terms of evolution, I was happy to see the AO7 video that Hans made, because we use some of the same stuff in there on the previous on Fox. We use the photon-powered rotation, and we use the magnetic attitude control. We don't on golf, but we did on Fox. And interestingly, we do have the another rod as well that's not a magnet, but I believe that the reason that we don't spin too fast is because the magnet is following the Earth's magnetic field. So as you cross over the poles, the satellite flips over. When the satellite flips over, the colored part that will rotate it tends to rotate it the other direction, so it slows it down, keeps it from going too fast. But it was very interesting to see how much even Fox, which was new to me entirely, depends on historical satellites like AO7, probably AO1 as well. So thank you very much for listening.